So far we have calculated the radiant heat exchange between black surfaces, two black surfaces at two different temperatures. And in the process of deriving expressions for the radiant heat exchange between two black surfaces, we have defined a term called as the shape factor. Now, today we would like to extend these ideas to first calculate radiant heat exchange rates in an enclosure consisting of a number of black surfaces. Consider the following enclosure as shown here. This is a 3 surface enclosure. It is shown as a cylindrical enclosure, but it could be any 3 surface enclosure. The surface 1 is this surface, surface 2 is this surface, and surface 3 is the round surface, the curved surface of the cylinder. Now, we are told in this case that the surface 1 is at a temperature T1, the surface 2 is at a temperature T2, is at a temperature means is maintained at a temperature T2, and surface 3 is an perfectly insulated wall. The curved surface is perfectly insulated. It has refractory material all around it and is perfectly insulated, and we call that as surface 3. All right. We assume arbitrarily that surface 1 is at a higher temperature than surface 2. It could be anyway, it just I am making just an assumption. Therefore, obviously, the surface 1 is going to be the surface at which heat is going to be supplied, and surface 2 is going to be the surface at which heat is going to be received, because it will be at a lower temperature. So, T1 is the temperature of surface 1 and T2 the temperature of surface 2. Q1 is the rate at which heat is supplied at surface 1 and Q2 the rate at which heat is supplied at surface 2. We would like to find in this case the values of Q1 and Q2 and also find what is the temperature attained by the wall 3, the curved wall 3. Now, I again repeat, although I have shown a cylindrical enclosure, it could be any 3 surface enclosure. It does not have to be a cylinder at all. All right. So, let me again just put that down, what is specified and what is to be found. In this particular case, T1 is specified, the temperature T1 is specified, surface 1 is maintained at this temperature T1, T2 is specified, and it is specified that at the surface 3 we have very good insulation. Therefore, it is specified that Q3, the rate at which heat flows at the surface 3 would be 0, because it is perfectly insulated. These are our specified quantities. What are we asked to find? We are asked to find Q1, the rate at which heat is supplied at the surface 1, in order that it should remain at the temperature T1, Q2, the rate at which heat is supplied at the surface 2, in order that it should remain at the temperature 2, and T3, the temperature attained by the surface 3, so that it satisfies the condition of being a perfectly insulated surface. All right. This is the problem as is posed. All the surfaces are black, I repeat. It is a 3 surface enclosure with all the surfaces black. Now, let us use the expressions which we have derived for heat exchange between black surfaces. In order to derive the expressions for Q1, Q2 and T3, let us use the expressions which we have derived earlier for heat exchange rates between two black surfaces. Q1, the rate at which heat is supplied at surface 1 is obviously equal to Q13 plus Q12, all right. And that in turn, what is Q13? Q13 is nothing but A1 F13 EB1 minus EB3. This is the expression which we have derived earlier, plus Q12 is nothing but A1 F12 EB1 minus EB2. I am writing EB1, EB2 and EB3 instead of writing everywhere sigma T1 to the power of 4 or sigma T2 to the power of 4 or sigma T3 to the power of 4. That is really what EB1, EB2 and EB3 represent. Instead of keeping on writing the bigger expression, I will write EB1, EB2, EB3. At the end, I will substitute the Stefan-Boltzmann law. All right. So, the rate at which I supply heat at the surface 1 must be equal to the heat exchange rate between 1 and 3 and the heat exchange rate between 1 and 2. All right. Similarly, Q2 must be equal to Q21 plus Q23, which is equal to A2 F221 EB2 minus EB1 plus A2 F23 EB2 minus EB3. And finally, for the surface 3 I can say Q3 is equal to A3 F31 EB3 minus EB1 plus A3 F32 EB3 minus EB2, and we know that Q3 is equal to 0. So, I have 3 equations now, the first this equation, the second equation and third equation. I have 3 equations and 3 unknowns. And what are my 3 unknowns? Q1, Q2 and EB3. EB3 is nothing but T3. Instead of writing sigma T3 to the power of 4, I am writing EB3. So, I have got 3 linear equations in 3 unknowns. Solve for them and I will get the quantities Q1, Q2 and EB3. So, it is a very straightforward problem which we have. If we solve these equations, we will get, now I am skipping a few simple algebraic steps and giving the solution. I am saying if we solve those 3 equations for the 3 unknowns Q1, Q2 and EB3, that is T3, we will get Q1 is equal to minus Q2, which is equal to EB1 minus EB2 into A1 F12 plus A1 F13 F32 divided by F32 plus F31, and the third unknown T3 will be equal to F32 T2 to the power of 4 plus F31 T1 to the power of 4 divided by F32 plus F31, the whole thing within square bracket to the power of 1 by 4. This is the solution to the problem. This is what we are looking for. So, you can see 3 surface enclosure where all the surfaces are black and the temperature is specified or the quantity Q is specified at that surface. Then we get as many equations as there are surfaces for the enclosure and we solve for the required number of unknowns. That is all that it really comes to. Now, in this particular case, as I said, this is a general situation that we have solved for. Suppose I have a 3 surface enclosure in which F1 to 1 is equal to F2 to 2 is equal to 0. That means, I have a 3 surface enclosure like the one I showed at the beginning. alright. That means the cylindrical enclosure which I showed. Let me show it again. Suppose I have such an enclosure in which 1 is a flat surface, 2 is a flat surface, and therefore, F1 to 1 and F2 to 2 are automatically 0. Let us say that is the enclosure that I have. Then one can in fact show quite easily that the expressions which we have derived for Q1 and Q2 will simplify to the following form, and this again is a matter of just a little algebra. So, I am skipping a few lines here. I would like you to proceed from the earlier solution, which I display again. This is the earlier solution. In this solution, add the extra knowledge that F1 to 1 and F2 to 2 are 0, all right, and then show that this solution reduces to this solution. Now, the simplified solution Q1 equal to minus Q2 equal to sigma into T1 to the power of 4 minus T2 to the power of 4 A1 within square bracket A2 minus A1 F1 to 2 the whole square divided by A1 plus A2 minus 2 A1 F1 to 2. Notice now the only unknown is F1 to 2. All other shape factors get eliminated because they are related in some way to F1 to 2 through the enclosure relationship which we mentioned earlier. And we can show further that T3 will come out to be equal to A2 minus A1 F1 to 2, the whole thing multiplied by T2 to the power of 4 plus A1 into bracket 1 minus F1 to 2, close the bracket T1 to the power of 4 divided by A1 plus A2 minus 2 A1 F1 to 2, the whole thing to the power of 1 upon 4. So, we get these simplified expressions if we have an enclosure in which F1 to 1 is equal to F2 to 2 is equal to 0. All right. So, we have a general situation which we have solved for. This is the more specific situation in which F1 to 1 is equal to F2 to 2 is equal to 0. Now, in order to just clear up ideas, let us do the following problem. I am going to solve the following problem, just to, it is really just a substitution. Let us say we have an enclosure like this. Let us say we have an rectangular enclosure like this. This is the rectangular enclosure that we have, all right. And in this rectangular enclosure, you are told that the sides are 1 meter by 2 meters. The sides of the horizontal faces are 1 meter by 2 meter and the vertical edges are all 4 meters, all right. You are further told, let us say that the top surface, the horizontal face at the top, this one, is the surface 1, this is the surface 1, maintained at a temperature of 200 degrees centigrade, 473 K. Let us say the horizontal face at the top, the 1 by 2 meter face at the top, which is maintained at a temperature of 473 K, is this one. Now, the bottom face, which I will shade again, this one, this is surface 2, this is surface 2 and this is at 100 degrees centigrade, that is 373 K. And you are told that the 4 vertical faces make up surface 3. The 4 vertical faces, that is these, the 4 vertical faces make up surface 3. 4 vertical faces make up that is a 3 surface enclosure now, because we are specifying the top horizontal face is surface 1, the bottom horizontal face is surface 2, and all the 4 faces together which are vertical make up what we call as a surface 3, and that is perfectly insulated. Therefore, for those 4 faces Q 3 is equal to 0, perfectly insulated surface. To find Q 1, Q 2 and the temperature attained by the surface 3, that is T 3. So, it is a direct substitution to the expression that we have just derived, all right. And the first thing we will need to know, of course, is the shape factor f 1 to 2 between the top face, the top horizontal face and the bottom horizontal face of this rectangular enclosure. So, let us first find out f 1 to 2. Recall in the previous lecture we had shown a figure in which the values of f 1 to 2 were plotted, right. So, what do we need for that figure? We have a situation of 2 parallel rectangles. This is a situation of 2 parallel rectangles of equal size. In order to read off the value f 1 to 2 from the available graphs, we need the values of L 1 by d and L 2 by d, and in this case L 1 by d will be 0.5, it is 2 by 4, and L 2 by d will be 1 by 4, that is 0.25. Okay. So, now go to the graphs. The graphs are, if you go to the available graphs, they are give the value of f 1 to 2 plotted. All we have is a plot like this. F 1 to 2 is plotted against L 2 by d, and there are different graphs like this for different values of L 1 by d. So, in this particular case, look up the value of go to the value of 0.25 here for L 2 by d. Okay. Go up vertically to the graph corresponding to L 1 by d equal to 0.5, then go horizontally, and this is our value of f 1 to 2. And in this particular case, we will get, if you look up the graphs, which I want you to do on your own, go to any textbook, any of the references that I have given you, and you will read off the value of f 1 to 2 in this case to be 0.036. Okay. Now let us substitute into the expression that we have for q 1 and q 2. We have also in this particular case A 1 is equal to A 2. So, since A 1 is equal to A 2, our expression for q 1 equal to minus q 2 in this particular case becomes sigma A 1 T 1 to the power 4 minus T 2 to the power 4 within square bracket 1 minus f 1 to 2 the whole squared divided by 2 into 1 minus f 1 to 2. All right. The earlier expression that I have given you, in that expression put A 1 equal to A 2 and you will get this for q 1 equal to minus q 2 equal to this. Now, note, I have not mentioned it earlier, but note q 1 is equal to minus q 2, it has to be, all right. Why? Because there are 3 surfaces making up the enclosure. In a steady state, Q1 plus Q2 plus Q3 must be equal to 0. The first law of thermodynamics requires that, right. Net rate at which heat enters through all the three phases must be equal to 0. Q3 is equal to 0 in this case, therefore, Q1 must be equal to minus Q2. Now, in this particular case, substitute now the given numbers. That means, substitute the value of sigma into A1, which is 1 by 2 into 473 to the power 4 minus 373 to the power 4, the whole thing into 1 minus 0.036 the whole squared, 2 multiplied by 1 minus 0.036, and if you calculate the value, you will get 1803 watts. So, the rate at which you supply heat at the surface 1 will be 1803 watts. The rate at which you extract heat at the surface 2 is 1803 watts, and that is what maintains the steady state in that enclosure. And further, if you calculate T3 in this case, you will get T3 is equal to, again making use of the fact that A1 is equal to A2, T3 becomes T1 to the power 4 plus T2 to the power 4 divided by 2, the whole thing to the power of 1/4. So, it is nothing but 473 to the power 4 plus 373 to the power of 4 divided by 2, the whole thing to the 1/4, which is equal to 432 Kelvin. T3 must be a temperature between T1 and T2, quite obviously. The surface 3 has to attain a temperature somewhere between the two extremes. 1 is the surface at which you are supplying heat, 2 is the surface at which you are extracting heat. Surface 3 must acquire a temperature in between, which in this case comes out to be 432 K. All right. So, that is the way we would use the results that we have got for the expression that we have just derived. Now, let us go on. Let us say, let me just change the problem a little and say, suppose I have some 3 surface enclosure. I am just drawing some arbitrary 3 surface enclosure like this. All right. Suppose I have a 3 surface enclosure of a given geometry. So, I can get the values of all the shape factors in that enclosure, and suppose the surfaces are maintained at temperatures T1, T2 and T3. The 3 surfaces are maintained at temperatures T1, T2 and T3. Okay. Calculate to find Q1, Q2 and Q3. Do this on your own, there is nothing to it. It is just the same earlier 3 expressions that we had, but you know now in this case the values of EB1, EB2, EB3. So, you can directly from 3 equations which I put down earlier get the values of Q1, Q2 and Q3. So, the point I want to make is, when you have for any one of the surfaces, you need to specify either the rate at which heat is supplied at the surface or the temperature of the surface, either the Q for the surface or the T for the surface. And you can find, if one is specified, the other can be found out, right. So, keep that always in mind. In any 3 surface enclosure, if I specify either Q or T for it, the other quantity which is not specified can be determined. That is basically what we can do with the help of the 3 equations for the 3 surfaces. And once I have said this for 3 surfaces, it is very obvious to you that I can extend these ideas to an n surface enclosure. I could have 4 surfaces, in which case I will get 4 equations. I could have 5 surface enclosure, in which case I will have 5 equations, and in each case ask yourself, is q specified or is t specified? Depending upon that, one is the known, the other is the unknown, and we solve for as many unknowns, as many q's which are unknowns or as many t's which are unknowns, given the other quantities which are given to, given the other values which are knowns. Okay. So, now basically we have got with a theory for calculating heat exchange rates in a black surface enclosure. We have really derived expressions for a 3 surface enclosure, but I think it is obvious to you that extending these ideas to a 4 surface or a 5 surface enclosure presents no real problems. The only thing we must be able to calculate is the shape factors for this enclosure. Whatever be the enclosure, you must be able to get the appropriate shape factors, then you can put down a set of equations and get the values of q or t for each surface of the enclosure. Now, we want to move on to enclosures which have gray surfaces, or rather diffuse gray surfaces. All right. Now, we want to go on to enclosures which have not black surfaces, but diffuse gray surfaces. And what we are going to do first is, we are going to calculate heat exchange rates by radiation in an enclosure which consists of only 2 surfaces. What are the 2 surfaces? 2 infinite parallel diffuse gray surfaces. We are going to consider such an enclosure which has 2 surfaces, and the 2 surfaces are 2 infinite parallel surfaces which are diffuse gray. We have taken a 2 surface enclosure because it is the simplest to handle first of all, and then we will go on to a few more complicated cases later. So, the first thing we are going to look at now is heat exchange rates by radiation between 2 infinite parallel diffuse gray surfaces, that is effectively a 2 surface enclosure made up of 2 infinite parallel surfaces. Now, let me just sketch the surfaces. Let us say these are 2 this is one surface, this is another surface. Okay. These are 2 diffuse gray surfaces, infinite surfaces parallel to each other, and obviously they make up a 2 surface enclosure because they are infinite in extent. I will call this as the surface 1 and I will call this as the surface 2. And let us say that the surface 1 is maintained at a temperature T 1, the surface 2 at a temperature T 2. These are diffuse gray surfaces, and further let us say they are opaque. Further, let us say they are opaque surfaces. Let the emissivities of these 2 surfaces, let the emissivities of these 2 surfaces be epsilon 1 and epsilon 2. Okay. It follows from Kirchhoff's law, since they are diffuse gray surfaces, that the absorptivity is also epsilon 1 and epsilon 2. Emissivity is equal to absorptivity because they are diffuse gray surfaces and opaque. If they are opaque, it follows that the reflectivity of these surfaces will be 1 minus epsilon 1 and 1 minus epsilon 2. So, let me write that also. The reflectivity of these two surfaces, this one will be 1 minus epsilon 1, this one will be 1 minus epsilon 2, because they are opaque. Therefore, absorptivity plus reflectivity must be equal to 1. So, this is the characterization of the surface. A two surface enclosure made up of two infinite parallel plates, diffuse gray surfaces, opaque surfaces, maintained at temperatures T1 and T2. Emissivity and absorptivities are epsilon 1 and epsilon 2. Reflectivities are therefore 1 minus epsilon 1 and 1 minus epsilon 2. We are required to find the rate at which heat is supplied at the surface 1, or the heat flux is supplied at the surface 1, and the rate at which heat is supplied at the surface 2, Q by A 1, Q by A 2, heat flux supplied at surface 1, heat flux supplied at surface 2. Obviously, I need not repeat what I have said earlier. Q by A 1 must be equal to minus Q by A 2, that is obvious. So, I will be getting both these, the values for both expressions for both these simultaneously. So, we want to find out expressions for Q by A 1, rate at which heat is supplied at the surface 1 and at the surface 2. Okay. Now, let us do the following. In order to derive this expression, let us consider the radiation going back and forth between these two infinite surfaces. We are going to consider radiation going back and forth between these two surfaces. Before I do that, let me first of all state, from the Stefan-Boltzmann law, the emissive power of surface 1 is epsilon 1 sigma T1 to the power 4, and the emissive power of surface 2 is epsilon 2 sigma T2 to the power of 4. Okay. So, I will keep on writing E1 and E2 for some time. Right at the end, I will substitute these expressions for E1 and E2. And as I said a moment ago, let me repeat, I am going to analyze what happens to the radiation which is emitted by one surface. Okay. What is going to happen is, any radiation emitted by say the surface 1 or the surface 2 will go to the other surface, get partly absorbed and partly reflected, will come back to the original surface where it will get partly absorbed, partly reflected, will again go back to the first next surface, partly absorbed, partly reflected. So, you will have successive reflections and absorptions as the radiation is bounced back and forth. Any radiation emitted from one surface bounces back and forth and is successively absorbed and reflected. We want to analyze in this manner. So, let us now look at the surface 1 and see how the radiation is absorbed and reflected. E2 is the emissive power of surface 2. So many watts per meter squared, let us say, is being emitted from this surface 2. This is the surface 2, all right. E2 is its emissive power. Now, I am showing one arrow here, but this arrow is symbolic. Actually, this radiation emitted from the surface 2, from this element here, is this radiation is really going off in all directions. Remember that, all right, because it is a diffuse gray surface. So, radiation is really going in all directions like this. All of it ultimately has to reach the surface 1, because 1 and 2 are infinite in extent. But I am just showing one arrow to say, to indicate symbolically radiation emitted by the surface 2. And what is its flux? Its flux is E2. So, let me draw it in bold letters here, E2, so many watts per meter square. This E2, when it ultimately reaches the surface 1, not by this arrow, but in any whichever direction it goes, ultimately hits the surface 1, it is going to get absorbed. And how much is going to get absorbed? What is going to get absorbed is epsilon 1 E2. That is the quantity that is going to get absorbed. What is going to get reflected is 1 minus epsilon 1 E2. That is the quantity that is going to get reflected. Okay. Again, out of this reflected amount, a certain amount will come back and get absorbed in the surface 2. What will that be? That will be epsilon 2 into 1 minus epsilon 1 E2. That is the quantity that will come back to the surface 2 and be absorbed by it. The balance will get reflected, that will be 1 minus epsilon 2 into 1 minus epsilon 1 into E2, that is this quantity, and so on. So, as you can see, as the radiation goes back and forth, we will have a certain amount absorbed, reflected, absorbed, reflected, absorbed, reflected, and so on. Okay. So, now you say to yourself, the radiant flux, if you take an algebraic sum of all this, you can say radiant flux emitted by the surface 2 and absorbed by the surface 1. If you ask yourself what is that amount, radiant flux emitted by 2, emitted by the surface 2 and absorbed by surface 1 will be equal to, the first term will be epsilon 1 E2. This is the first quantity. E2 is emitted, epsilon 1 into E2 is absorbed by the surface 1. Now, again comes back to surface 2, is reflected from surface 2, again gets absorbed, plus the next quantity is going to be epsilon 1, 1 minus epsilon 2, 1 minus epsilon 1 E2, plus the next quantity is going to be epsilon 1, 1 minus epsilon 2 the whole squared, 1 minus epsilon 1 the whole squared into E2, plus, you understand, that is how we are going to get an infinite geometric progression series, which is equal to, let me just put it properly, this is equal to E2, I will take that outside, that is a common factor, I will take epsilon 1 outside, that is common, and I will get 1 plus 1 minus epsilon 2, 1 minus epsilon 1 plus 1 minus epsilon 2 the whole squared, 1 minus epsilon 1 the whole squared, plus so on. And if I sum up this geometric progression within the square bracket, I will simply get E2 epsilon 1 1 upon 1 minus epsilon 2 1 minus epsilon 1. This is the radiant flux emitted by surface 2 and absorbed by surface 1. And I can simplify that expression a little further and say this is further equal to, on simplifying, E2 epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. That is what it will simplify to, which you can check yourself. Okay. So, this is the radiant flux emitted by surface 2 and absorbed by surface 1. Now, in a similar manner, we can find the radiant flux emitted by surface 1 and absorbed by surface 2, right. If you do that, you will get E1 epsilon 2 divided by epsilon 2 plus epsilon 1 minus epsilon 2 epsilon 1. That is what you will get. All that I have done is I have replaced in the previous expression which we derived, I have replaced 2 by 1 and 1 by 2 and I will get this. I do not need to really derive it and go through a geometric progression. Okay. So, I have now two expressions, the radiant flux emitted by surface 2 and absorbed by 1, the radiant flux emitted by surface 1 and absorbed by surface 2. I take the difference of the two and that is the radiant heat flux exchange between surface 1 and surface 2. So, we will get the radiant heat flux exchange between surface 1 and surface 2 will be given by, let us put that down now. Therefore, the radiant heat flux exchange, net exchange of radiant heat flux, net exchange of radiant heat flux between 1 and 2 between the surfaces 1 and 2, which is nothing but q by a 1 to 2 will be equal to the difference of the two expressions we had earlier. So, I am going to get E 1 epsilon 2 minus E 2 epsilon 1, the whole thing divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. And now, if I write the full expressions for E 1 and E 2, that is epsilon 1 into sigma into T 1 to the power of 4 and epsilon 2 into sigma into T 2 to the power of 4, I will get this is equal to sigma epsilon 1 epsilon 2 T 1 to the power 4 minus T 2 to the power 4 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2, which I can write further as sigma into T 1 to the power of 4 minus T 2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the expression that we get for Q, the heat flux, net radiant heat flux exchange between the surface 1 and the surface 2. Okay. Now, there are only two surfaces in this enclosure. So, if there are only two surfaces, the net radiant heat flux exchange between the two surfaces is equal in magnitude to the net radiant heat flux leaving either of the two surfaces. All right. So, in this particular case, since there are only two surfaces involved, q by a 1 2 must be equal to q by a 1, which in turn must be equal to q minus q by a 2, and that in turn is equal to sigma T 1 to the power of 4 minus T 2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this is the expression that we are looking for the heat supplied or the heat flux supplied at the surface 1 or at the surface 2. And this is a rather well known expression. You should know this. anyone studying radiation has to know this expression, the radiant heat flux exchange between two diffuse gray surfaces constituting a system of infinite parallel plates. All right, now we want to look at a problem. We are going to look at the following problem. We will say, suppose I have a surface 1 and a surface 2 like this. This is surface 1 and this is a surface 2. Surface 1 is maintained at a temperature T1, surface 2 is maintained at a temperature T2. Okay. They are a system of infinite parallel plates. We know the expression for heat flux exchange between these two surfaces. By the way, this is the radiant heat flux exchange. So, in all this we have assumed that there is a vacuum between these two infinite parallel plates. We have not looked at any convective heat transfer. So, keep in mind we are doing all these calculations as if there is a vacuum in the space between the infinite parallel plates, or there is a vacuum in the black surface 3 surface enclosure which we considered earlier. Now, in this system, let us say we insert a third plate like this in between. Let us say I have insert between these two a third plate 3, which is a thin opaque infinite, a thin opaque infinite plate. Let us say I insert between 1 and 2 a thin infinite opaque plate 3, and let us say that its emissivity on both surfaces is E3. It is a gray surface, diffuse gray. Surface 1 and 2 are diffuse gray of course. So, their emissivities are epsilon 1 and epsilon 2. So, in between you insert a thin opaque infinite plate which is also diffuse gray and has an emissivity epsilon 3. Now, what is to find Q by A 1? That is the problem. This thin opaque infinite plate incidentally is often referred to as a shield. It is something between 1 and 2. So, it is like a shield. Now, it is quite obvious that the shield will acquire a temperature T3. The shield will acquire a temperature T3 such that Q by A1 will be equal, Q by A 1 to 3 will be equal to Q by A 3 to 2. Do you follow? That is what is going to happen in the steady state. If I put a shield in between, 3 will acquire a temperature T3 such that the net heat exchange between 1 and 3 is equal to the net heat exchange, radiant heat flux exchange between 3 and 2, right. Now, we can put down expressions for these quantities, we have just derived them. What is Q by A 1 to 3? Q by A 1 3 is equal to sigma, the expression that we have just derived, T1 to the power of 4 minus T3 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1, and Q by A 3 2 is equal to sigma T3 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay. and q by a 1 3 and q by a 3 2 are equal. And what are they equal to? They are nothing but equal to q by a 1, which is what we want to solve for. So, we have got two equations now, which we have to solve for q by a 1 and for T 3. Okay. We got two equations which we want to solve primarily for q by a 1, but we could also get the value of T 3. So, since we are interested in q by a 1, eliminate T 3 to the power of 4. Now, I am skipping a few steps. That means, you will have to write this as T 1 to the power of 4 minus T 3 to the power of 4 equal to something, and this equation you will have to write as T 3 to the power of 4 minus T 2 to the power of 4 equal to something, and then add the two expressions, in which case you will eliminate T 3 and you will get, I will just put down the final expression, you will get 1 upon sigma q by a 1 into 1 by epsilon 1 plus 1 by epsilon 2 plus 2 by epsilon 3 minus 2 is equal to T 1 to the power of 4 minus T 2 to the power of 4. That is what you will get. Or finally, if you want an expression for q by a 1, you will get q by a 1 is equal to, in this case, q by a 1 is equal to sigma into T 1 to the power of 4 minus T 2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 2 by epsilon 3 minus 2. That is the final expression for the heat flux, the rate at which heat is supplied at the surface 1, or this is also equal to minus q by a 2. Okay. Now, consider the special case if epsilon 1 equal to epsilon 2 equal to epsilon 3. In this case, then q by a 1 is equal to sigma T 1 to the power of 4 minus T 2 to the power of 4 2 times 2 by epsilon minus 1. Okay, that is what you will get. What you have got really is, if the epsilons are all equal, what in effect you are saying is q by a 1, that is what you are saying is q by a 1 with one shield is equal to half into the value of q by a 1 without a shield. That is what you are getting. With one shield, the value of q by a 1 is reduced by half, 1 by 2. Extend this on your own now. Suppose I have 2 shields instead of 1. What result will you get? Show that you will get 1 by 3 instead of 1 by 2. If you have n shields, you should get 1 upon n plus 1 into the value of q by a 1 without a shield. So, a shield, one shield reduces the value by half, 2 shields reduce the value by 1 by 3 to what you would get, to the value you would get without a shield. So, that is the special case if of course epsilons are all equal.